Hello all, my name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I'm creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, in this particular lecture, we're going to discuss about delta modulation. These are the outlines. We'll start up with the introduction, where we will discuss whatever we have learned in our earlier lectures, such as our differential pulse code modulation. Then we're going to discuss the basic principle of delta modulation, which will be followed by delta modulator transmitter as well as receiver. Then we will going to discuss several advantages of delta modulation schemes, which will be followed by various drawbacks of delta modulation. And finally, we will going to conclude by discussing some of the applications of delta modulation. So delta modulation is a differential pulse code modulation schemes in which the difference of the signal is encoded into just one bit. In differential pulse code modulation system, we had already studied that in DPCM, we are basically encoding the difference between the current sample value and the previous one. Here also we are employing the same principle, but here the difference is in delta modulation, we are only encoding this difference of the signal into just one bit. So in that essence, we could say that it is very bandwidth conservant scheme. We can also consider it as the extension of differential pulse code modulation and the PCM system. So it performs better than the PCM and differential pulse code modulation in terms of bandwidth or data rate requirement, as it is having large information carrying capacity with the use of fewer bits. We had already mentioned that in delta modulation, we are only encoding our complete information into just a single bit, whereas in PCM, we will be having lots of redundancy, and in DPCM, somehow we have reduced the redundancy via transmitting the difference of the signal rather than transmitting the complete sample value. But obviously, when we are talking about delta modulation and we are only transmitting only a single bit, then obviously the bandwidth requirement or the bit rate requirement will be very low in comparison to PCM and DPCM. So now we're going to discuss the principle of delta modulation. It is the technique which provides the staircase approximation to an oversampled version of the message signal, that is our analog input signal. So what do you mean by staircase approximation? This would be explained by the figure in the next slide, but one important thing here is oversampled version of the message signal. I mean, the sampling rate we will be having here in delta modulation will be greater than or equal to twice of the FM. So what is the benefit of having oversampled version of the message signal? Obviously, if we are taking oversampled version of the signals, the consecutive samples are highly correlated, or they are almost equivalent to each other. So this property we will going to exploit in our delta modulation scheme. So in the linear delta modulation, the approximated staircase version of the sampled signal is compared with the original signal, or we could say that the current sample value, and the difference signal is produced as we did in our DPCM systems. So what we will going to do that we will going to compare the staircase version of the signal with the current sample value of the signal, and we will going to pass that difference of the signal obviously after quantizing. But here the important point is that difference that we are transmitting through the delta modulator encoder will only going to contain single bit. So the difference signal is then quantized into only two levels, that is plus minus delta, corresponding to the positive and negative difference respectively, as we had already discussed. So here the important point is whatever be the value of error, we are not at all passing the exact value of the error signal. We will be going to quantize our error value only into two levels, that either the error signal will be plus delta or it will be minus delta, and we are only passing only those two levels. So this particular figure shows the process of delta modulation. We are assuming linear quantization where the step size is delta, and this duration is our sampling duration, or we could say it is our sampling period, which is denoted by TS. And by staircase means this one, we are actually trying to approximate our signal with the help of these staircase, and these staircase are actually following the input signal value. So these are known as our staircase approximation. So this is our continuous time signal or message signal XT, and this staircase would have been denoted by this ut. So on the x-axis we will be having time, and on the y-axis we will be having amplitude. So what we actually doing in our delta modulation is we are comparing the previous approximated value and the current sample value of my signal. If the current sample value of my signal is lesser than the previous approximated value, then 0 bit is transmitted, and if the current sample value of my signal is greater than this previous approximated staircase version of the signal, then 1 bit would have been generated. So we could understand it via some example. Let us say this is the previous staircase approximated value of our signal, and this is the current sample value of my message signal. So obviously this current sample value of the signal is greater than this previous approximated staircase version of my signal, then 1 bit is transmitted. Then in the next cycle again we will going to compare this previous approximated staircase version of the signal with the current sample value. In this case also current sample value is greater than our previous approximated staircase version of the signal, then again bit 1 is get generated. So here in this example we are saying that 1 bit or 0 bit is generating, but actually what is happening in our delta modulator is it will going to compare the current sample value of the signal with the previous approximated staircase version of the signal. If the current sample value is greater, then obviously for our staircase version we must have to increase the step size delta in order to map our signal properly. So it will basically going to generate an error signal analogous to plus delta, and in the reverse case it will going to generate minus delta. So these bit would actually being generated by our encoder depending upon the quantized version of our signal. I mean for plus delta we'll be having 1, and for minus delta we'll be having 0. So this we will going to discuss in our upcoming slides. So if the approximated signal lies below x of nts, then the approximated signal is increased by plus delta as we had already discussed, and vice versa. I mean if the approximated signal value lies above x of nts, then minus delta will get generated. So this scheme works well for small changes in the signal values between the samples. Hence sampling is done at rate higher than the Nyquist rate. So obviously we could say that if sampling would have been done at the rate lower than the Nyquist rate, then the signal changes might be large and we are not in a state to approximate our signal well. So it aims at increasing the correlation between the adjacent samples. So we are increasing the correlation via performing sampling at greater than the Nyquist rate. If the number of samples are very close apart, then the amplitude variation will be quite lower. So we could say that they are almost signifying same amount of information, or we could say that they are highly correlated. So this particular figure shows the delta modulation encoder operation. So here we'll be having input sample value of the signal that is represented by x of nts, and the next input to the summer is the approximated staircase version of the signal. So we will going to have the difference between these two signals in order to get the error signal. So this is with the negative sign, and the difference is called as your error signal, which is denoted by E of NTS. Then this error signal would have been passed through a 1-bit quantizer. Then what will 1-bit quantizer will gonna do is it will going to quantize our error signal either in the form of plus delta or minus delta. Then depending upon this quantized value of error signal, our encoder will going to generate bits either 1 or 0. As we have discussed, for plus delta encoder is generating 1, and for minus delta encoder is generating 0. So how we're going to have this current staircase value of our signal? It is the summation of error signal EQ of NTS plus the previous value of our staircase approximation version of our signal. Then we're going to pass it through a delay. So this will going to give us a signal value equivalent to U of n minus 1 TS, or we could say that the previous value of the approximated version of staircase. Then again this will get feedback this summer, which will going to generate error signal. Then this process will keep going on. So this is our accumulator, which consists of this delay element and summer. So accumulator will going to accumulate or contain the previous staircase version of our signal. So this is how our delta modulator encoder works. Now we're going to discuss in greater detail. So here is the mathematical explanation. Error signal would have been calculated as x of NTS minus x cap of NTS, where this x cap of NTS is nothing but it is the last approximated staircase waveform, and x of NTS is the current sample value. The difference between these two is denoted by E of NTS, as we have discussed in our block diagram. So these are the descriptions of various values that we have discussed. So if U of NTS is the present sample approximation of the staircase output, then U of n minus 1 TS, or we could say that it basically represents the previous sample approximation of staircase output, which is equivalent to x cap of NTS, or we could say that x cap of NTS represents the last sample approximation of staircase output. EQ of NTS would have been defined as it will be equal to delta times of sine of E of NTS. What will be the outcome of sine of E of NTS? So it is a function whose value will be +1 or -1 depending upon the value of E of NTS. I mean, if the error is positive, then this sine of ENTS outcome will be +1, and if error is negative, then the value of this sine of E of NTS will be equal to -1. We have already defined that E of NTS will be given as x of NTS minus x cap of NTS. So if error is positive, then EQ of NTS will be plus delta, and if error is negative, then EQ of NTS will be equal to minus delta. So the present transmitted signal turns out to be U of n minus 1 TS plus the quantized error version of our signal. So this is the relationship that we are referring while discussing the principle of delta modulation. So we will just going to add plus delta or minus delta with the previous approximated value of our staircase version in order to get the current staircase approximation of our signal. So this particular figure shows the delta modulator receiver block structure, or we could say that delta modulation decoder. So obviously at the input side we'll be having certain bits in the form of 0101, and depending upon those bits value, this decoder will going to decode those bits and will going to generate quantized value of our signal in terms of plus delta or minus delta. So this decoder output will get fed to a summer whose second input is the delayed version of our staircase. So when we're going to combine quantized value of error signal and the previous staircase version of the signal in the combined fashion, they will going to generate the current staircase value of our signal. So when we will going to pass those staircase version of the signal through the low pass filter, we will get the smoothened waveform analogous to the input signal. So this is how we will going to regenerate our signal. So in delta modulation, the input is passed through the accumulator, which creates the staircase approximation similar to the transmitter side. Here important point is this accumulator is functioning same as the accumulator is working at our transmitting side. I mean, they are analogous to each other. So the accumulator output is then passed to the low pass filter to produce the original signal. So low pass filter is doing nothing but it is going to smoothen out our figure. Basically what it actually doing is we will be having this type of staircase version to the input of this low pass filter, and what does this low pass filter is going to do is it will going to smoothen out this waveform, and this is how we will going to receive our original signal back. So now we're going to discuss the advantages of delta modulation. So obviously the signaling rate and the transmission channel bandwidth is quite small in comparison to PCM. As in PCM, we are basically transmitting each and every sample value with the complete code words. But here in this delta modulation, we are only transmitting single bit. So obviously the signaling rate and the transmitting channel bandwidth is quite lower. So delta modulation works with lower channel bandwidth. This makes the system cost effective and simple to implement. About The channel bandwidth we had already discussed. This makes the system cost effective as well as simple to implement. So the feedback mechanism present in the modulation system ensures the quick as well as the robust delivery of the data bits. Obviously, the feedback mechanism ensures that the delivery of data bits are quite robust. So now here are certain disadvantages of delta modulation. So this basically has two drawbacks. Number one is your slope overload distortion, which is also called as startup error. And when it will going to happen is this distortion arises due to the large dynamic range of the input signal. I mean the input signal variation is quite larger, as well as there exists a rapid signal variation in the input signal. And second one is the granule noise, which is also called hunting. So this basically happens when the step size is too large in comparison to the small variation in the input signal. I mean if our input signal is varying very slowly in comparison to the step size. So obviously in that particular case, the error signal will be very high. So this particular figure shows the slope overload distortion. We had already mentioned that this basically going to happen when signal changes very rapidly. So this basically showing the rapid variation in our input signal, and our staircase will not in a state to predict that properly, or we could say that here step size delta is very small. So how we can reduce this slope overload distortion? Obviously via increasing our step size delta. So if we're going to increase the step size delta, the error between the actual signal and the staircase approximated version of the signal will get minimized. To reduce this error, the step size should increase when the slope of the signal is high. So obviously we could say that if the slope of the signal is quite higher, then we need to increase the step size. So here what do we mean by slope? Slope is nothing but it is basically dy by dx, or it would have been considered as amplitude variation divided by this time variation. So if we could say that this is the amplitude variation, which is denoted by a, and this is the time variation, which is denoted by ts, then the slope would have been given as a upon ts. So obviously if this slope is higher, then we should increase the step size in order to map the exact value or the actual value of the signal in order to minimize the error. Second one is the steady state, or we could say that granule noise. It is also called as hunting noise. We had already discussed that this error is basically going to happen when the signal variation is very low and the value of step size delta is much larger, or we could say that the step size will not be able to approximate these small variation and there always exists a difference. So this difference is nothing but it is an error, and that error is actually being called as your steady state error or granule noise. So when the input signal is almost flat, the staircase signal is keep on oscillating by plus minus delta around the signal, as denoted by this particular figure: plus delta, plus delta, minus delta. And the difference between the staircase version of the signal and the current sample value of the signal is quite higher. So how we can reduce this granule noise? Obviously, if we're going to reduce the step size delta, then this error will get minimized. So this error is minimized by making smaller step size, we had already mentioned. As we have seen that the delta modulation suffers with the slope overload distortion and hunting, and both of these noise can be contained or they could be reduced if we use some adaptive mechanism to select the step size. I mean for slope overload distortion, we need to increase the step size delta, and to contain our granule noise or steady state noise, we have to reduce the step size delta. So obviously if we could use some adaptive mechanism which could automatically select the step size where we have rapid fluctuation or variation or input signal, it could automatically increase its step size delta, and when we'll be having lower signal variation, it will automatically reduce the step size value delta, so that we could contain both these errors. So the solution is adaptive delta modulation, which will adaptively do the same thing that we have discussed. I mean when the signal variation is larger, it will going to increase the step size, and when the signal is almost constant, or we could say that it is having lower variation, then it will going to reduce its step size. So that adaptive delta modulation we're going to discuss in our next lecture. So at last we're going to discuss some of the applications of delta modulation. So what are they? Voice transmission systems such as telephone and radio communication, they will highly prefer this modulation schemes just because it is very bandwidth efficient scheme. It can carry larger amount of information with very fewer number of bits. So we could say that it is also behaving or acting like a compression mechanism. So our voice transmission systems such as telephones and radio communication, they are using this delta modulation. So this modulation is also applied to the electrocardiogram waveform for database reduction and real-time signal processing. This is basically a medical application. So this type of application basically require a robust mechanism which can convey larger amount of information with minimum number of bits. So delta modulation is also applied in television systems too. So these are some of the applications of delta modulation. These are the references. Thank you very much for your patient hearing.